Hello, welcome to the class. Today we're going to talk about section 1.1, real numbers. Now, the real number set can actually be broken down into many different sets. We're going to cover four in particular, namely the natural numbers, denoted with an. The natural numbers are counting numbers, 1, 2, 3, and so on. And you have integers, denoted with a z, and these are your positive and negative whole numbers, and 0. Then we have our rational numbers, denoted with a q, and some examples of rational numbers are 1/3, -4/5, -21/101. Any number that can be expressed as a ratio of two integers. And then we have irrational numbers. We generally write this as the real number set minus the rational number set, so r minus q in this way. Now there's a few formulations of this. Do a couple examples first here of what an irrational number looks like. For the square root of 2, pi, e, cube root of 2 as well. These are irrational numbers. And there are a few formulations that we use with the irrational numbers. Any real number that cannot be expressed as a ratio of two integers. This formulation you've probably heard more. Any real number with an infinite non-repeating decimal. And let me give you an example of this second formulation. 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if this is your decimal, you just keep on writing all these numbers in order, all the natural numbers in order behind a decimal. You'll clearly have a non-repeating decimal that will go on forever. So this is an irrational number. Now you might try to do one like this. Demonstrate an irrational number in the form of an infinite, non-repeating decimal using only two numbers. There's infinitely many solutions to this. Do an example. Classify each of the following into their respective sets. So here we have a, 3, b, square root 4, c, square root 3, d, 29/7, e, 1/3, and f, pi/4. All right. So a, I think everyone can look at this and say this is definitely an integer. It's an integer, but it's also a natural number. It's one of the counting numbers, so it is both of these. Square root of 4 reduces to 2, so it's also an integer. Natural number as well. If this was a negative, then it would only be an integer. But since they're both positive, we have integers and naturals. The square root of 3, this is an irrational number. There is no way to describe the square root of 3 as a fraction of two integer numbers. So this is irrational. D is rational. This is clearly a rational number because it is the quotient of two integers. Similarly, E is also rational. And F is irrational. Though it might look like a rational number, pi is not an integer. And since it's not an integer, this number is not a rational number in that sense. So pi is also an irrational number. Therefore, you have a rational or an irrational number overall. The next thing we're going to talk about is the Properties of real numbers. So first things first, we have the commutative property of both addition and subtraction, or additive commutative property would look like this. A plus B is equal to B plus A. And we have an example of this. A 3 plus 2 is equal to 2 plus 3. And our description over here. Any two real numbers can be added in any order. We have our commutative property of multiplication. A times B is equal to B times A. It will look like this. 7 times 2 is equal to 2 times 7. Any two real numbers can be multiplied in any order. The associative property. Associative property of addition. A plus B plus C, where we add A and B first, is equal to A plus B plus C, where we add B and C first. We have our example. 3 plus 4 plus 1. That'd be 7 plus 1 is equal to 3 plus 4 plus 1. And our description. When adding three numbers, it doesn't matter which two are added first. Now our associative property of multiplication. Looks very much the same. A times B times C is equal to A times B times C, where of course the parentheses are resolved first. 2 times 4 times 6 is equal to 2 times 4 times 6. When multiplying three numbers, it doesn't matter which two are multiplied first. And our final property is going to be our distributive property. So A times B plus C is equal to A times B. It's A times C. And this looks like it's 3 times 4 plus 2 is equal to 3 times 4 plus 3 times 2. The second distributive property is B plus C times A is equal to B times A plus C times A. 4 plus 2 times 3 equal to 4 times 3 plus 2 times 3. And the description is the same for both of these. When we multiply a number by a sum of two numbers, we get the same result as if we multiplied the number by each of the terms in the sum and added the result. Go ahead and do an example here. I want you to try one on your own. Use the distributive property to expand the expressions. For part A, you just need to use the distributive property once. For part B, you'll need to use the distributive property twice. Next, we're going to get into addition and subtraction. So I want to make a note here. The operators that we most commonly use are addition, subtraction, multiplication, and division. Let's start with the definition. This is important because I don't like the way that the book defines these. An identity is a number that leaves unchanged every other number when a specified operator is applied. Now, this is important that we specify an operator because identities change when you change an operator. For instance, the additive identity, notice that I specify additive, meaning we're talking about the operation of addition, is the number 0. Why is that? Well, a plus 0 is always going to yield a. No matter what a is, 0 doesn't change the value of a when you add them. So under the operation of addition, the number 0 doesn't change any other number. So it's the identity. It's called the additive identity. Maybe think on what the multiplicative identity will be. We're going to get to that in a bit here. Definition. The inverse of a number a when using a specified operator is the number that results in the operator's identity when the operator is applied to a and its inverse. I realize this might be a little bit confusing. I'm going to show you what the additive inverse of a is. The additive inverse of a is negative a. Because when we add negative a to a, the result is the additive identity, noting that the additive identity is 0. So when we're given a number a, to find that the additive inverse, we need to find the number that when we add it to the number a, we get back to the additive identity. So negative a for addition. Now, again, with the multiplication operator, try to think about what the multiplicative inverse will be of a number a. Again, we will cover that in a bit here. Note that you probably know already, subtraction is the inverse operation of addition. Basically, what this is saying is that subtraction undoes addition, just like division undoes multiplication. Properties of negatives. And example 1. Negative 1 times the number a is equal to negative a. Negative 1 times 2 is, of course, negative 2. Negative a is equal to a. Negative 3 is 3. Negative a times b is equal to negative ab. It's also equal to a times negative b. Negative 4 times 5 is equal to 4 times negative 5, which is equal to negative 20. Negative a times negative b is equal to positive ab, because the negatives will cancel. Negative 6 times negative 7 is equal to 6 times 7. 42, of course. 5. Negative a plus b is equal to negative a minus b. Negative a plus 9 equal to negative 8 minus 9. Which moves more negative? Number 9. 6. Negative a minus b equal to negative a plus b. Whenever we have a negative out front, you want to think of it as a negative 1. And it distributes to each of these. Now we talked about the distributive property earlier. So we would distribute this in to both, get a negative 8 and a negative 9. Similar here, we get a negative a and we already have a negative b, so we would get a negative b, which gives us a positive b. So -2, +3. So let's talk about the multiplication operator now. An identity is a number that leaves unchanged every other number when a specified operator is applied. Now we're going to talk about the multiplicative identity. And if you haven't figured it out yet, the multiplicative identity is 1. Why? Why is the multiplicative identity 1? Well, 1 multiplied by any number leaves that number unchanged, thus fitting the definition of identity. So the 1 is the multiplicative identity. And now you probably realize, or maybe you realized before, that each operator has its own identity. So when we go in through mathematics and you become more and more mature in your mathematical careers, you'll see different operations, and we will figure out those identities of those operations as usually as properties, just like we're covering now. The multiplicative inverse of a is 1 over a. Now, that's because when you multiply a times 1 over a, the result is 1, the multiplicative identity. We're not trying to get to 0, because 0 is the additive identity. We're trying to get to the multiplicative identity because that's the type of inverse we're looking for. And as a note, division is the inverse operation of multiplication. As I noted before with the addition, subtraction being the inverse operation of addition, division is the inverse operation of multiplication, means that division undoes multiplication. So if you multiply two numbers together, you undo that by dividing it. A fraction, a over b, is known as the quotient of a and b, where a is the numerator and b is the denominator. And the denominator is also called the divisor. Properties of fractions. 1. A over b times c over d is equal to a times c over b times d. Example of this, and a description. Example, 2 over 3 times 4 over 5 is equal to 2 times 4 over 3 times 5. When multiplying fractions, we multiply the numerators of each and denominators of each. A over b divided by c over d is equal to a over b times b over c. So if you had instead 3 divided, if we had 2 divided by 3 divided by 4 over 5, we would actually get 2 times 5 divided by 3 times 4. When dividing fractions, we invert the divisor and multiply. A over c plus b over c is equal to a plus b over c. 2 over 3 plus 4 over 3 is equal to 2 plus 4 over. So when we add fractions with a common denominator, we don't change the denominator. The denominator remains the same. A over b plus c over d is equal to ad plus bc over bd. Now, this might look a little bit complicated. It's actually not as bad as you think. And you've probably done this before. You need to find a common denominator first. 2 times 5 plus 3 times 4 over 3 times 5. When adding fractions with different denominators, find a common denominator, then add the numerators. AC over BC is equal to A over B. This will look like this if we have 2 times 4 over 3 times 4, then the 4s are common, so we can actually cancel them. And we just and 2/3 remains. Cancel terms that are common to the numerator and denominator. Now, I do need to make a note here. You need to notice that we are multiplying the 4 times the 2 and the 3 times the 4 here. So the 4 is being multiplied by the entire numerator, and the 4 in the denominator is being multiplied by the entire rest of the denominator. Now, since we are multiplying and dividing the same thing, those two operations will undo each other. So if we take something and divide by 4 and then immediately multiply by 4, that will revert back to what we had originally. Similarly here, we do 2 times 4 and 3 times 4 and then divide their results. The 4 will cancel itself, and you're left with 3 halves because multiplication and division undo each other. They're inverse operations. Okay, 6. If A over B is equal to C over D, then AD equals BC. Two over 3 equals 4 over 6. This implies then that 6 times 2 equals 3 times 4. Okay, and generally most of you know that this is cross-multiplying, but you have to be careful. You can only cross-multiply over an equal sign. Do an example. X over 3 plus 2 over 3. What will that equal according to the properties? B. X over y plus 3 over 4. What will that equal according to the properties? B. X over y divided by 3 divided by 4. What will this equal according to the properties? Well, this first one is pretty straightforward. We have a common denominator already. So all we do is add the numerators. Now, I want to emphasize here that when we have equality, going one direction is the same thing as going the opposite direction, because equality is both ways. It's bidirectional. So we can go from the left side to the right side, or we can go from the right side to the left side when it suits us. Most of the time, we will be going from left to right for this particular example or this particular type of problem. But every once in a while, it will benefit us to go from the right side to the left side. And we'll be able to break up a sum over, break up a fraction into 2 fractions over a sum in the numerator. Now, you can't do that in the denominator, but you can do that in the numerator. Part B, we're adding 2 fractions, but they have different denominators. So we need to find a common denominator. So we do x over y times 4 over 4. Because this denominator is missing the denominator over here. Similarly, this denominator is missing the denominator over here. So we need to multiply the second fraction by y over y. So now we have 4x over 4y plus 3y over 4y. And you can see that we have a common denominator now. And it reverts to a problem of like type A. Here, we have 4x plus 3y over 4y. When you have a common denominator, remember the denominator doesn't change. Now, the second one, or part C, is written a little bit differently than how I wrote it in the properties. You have one fraction divided by another fraction. Right, I want to show you why we invert the divisor and multiply. So x over y divided by 3 over 4. Now what I'm going to do is what I did up here to find a common denominator. I multiplied top and bottom by 4. Now remember, 4 divided by 4 is 1. And remember also that 1 is the multiplicative identity. So if I multiply x times y by the multiplicative identity, I haven't changed anything, because a multiplicative identity doesn't change anything when you multiply it. Okay, so we're going to do something similar here. We're going to multiply by a clever form of 1, namely the divisor inverted. 4 divided by 3, 4 divided by 3. So notice that 4 divided by 3 divided by 4 divided by 3 is 1. So I'm taking this huge fraction here and I'm multiplying it by 1, thus not changing the value of the problem. But I am going to change the form, as you can see. We have 4 times 3 divided by 4 times 3. So what we're going to get here is 12 divided by 12 in the denominator, which is 1. And in the numerator, we get 4x divided by 3y. This cancels to 1, of course, so we can just ignore it completely, and we're just left with 4x over 3y. Okay, the next thing that we're going to cover is the real number line. And many of you have probably seen it already. It's an infinite line in a single dimension. Generally, we write 0 in the middle. It doesn't have to be. We can draw whatever portion of the line that we need. But this line is a representation of all the real numbers in order. Now, since 0 is in the middle, that means that on the left we have negative numbers because they're less than 0, and on the right we have positive numbers since they're greater than 0. And we just go in order with equal spacing for equal measurement, like this. Now, these numbers are not the only numbers on the line. These, so far, the ones that I've actually drawn, the ones that I've labeled, are just the integers. Remember, we also have rational numbers and irrational numbers that are within this line. So here would be 1/2. And then here would be 3/2. Here would be 1/4. And so on. They are also in order according to size. Similarly, we have irrational numbers. Now, irrational numbers will look like this. Square root 2. And then if I draw a 3 out here, give you pi out here. And then e would be 2.71, right about there. This would be e. These are irrational numbers. Now, the origin is the 0 point. A is less than B if A lies to the left of B on the number line. So if we're looking at the number line here, we could say that the square root of 2 is less than e. Also say -1 is less than pi. We could say 3 is less than pi because it lies to the left of pi. Similarly, we say that b is greater than a if b lies to the right of a. So just like we said that 3 is less than pi, we can say that pi is greater than 3, or pi is greater than 0, or square root 2 is greater than -2, because it lies to the right. Example. Square root 2 is greater than 1. -1/4 is, of course, less than 0. Pi is greater than 3. -2 is less than -square root 2. I think this one is actually important. I'm going to go over that one. E -2 is, of course, less than -1. So this one's important because students mess this one up all the time. I didn't plot this. I didn't plot the negative square root of 2. Plot that really quick. Notice that -2 lies to the left of negative root 2. -2 lies to the left of negative square root 2. That means that -2 is less than negative square root 2. Similarly, it means that negative square root 2 is greater than -2. I want you to try one. Is -1 greater than -1000, or is -1 less than -1000? Okay, so now we're going to talk about sets and intervals. We've already discussed a few sets, namely the real number set, the natural numbers, the integers, the rationals and irrationals. But let's get into what a set actually is. Definition. A set is a collection of objects called elements. If an object is in a set S, we write A is in S. If an object is not in a set S, we write A is not in S. And we could do an example of this. It just looks very much like the sets that we've used already. We know that 3 is an integer, so we can write that 3 is an element in the integer set with this sort of little funny e. It's a form of an epsilon. And then we know that square root 2 is an irrational number, so it is not in the rational set. Okay, so now what I'm going to talk about is the forms that we write sets in. Some sets can be written as a list of elements. So S will equal 1, 3, 5, 7, 9. So sets like this we generally write when the set has a small number of elements. S is in set builder notation if S equals X such that X is an odd integer and X is between 1 and 10. Now I note here that we have less, or X is greater than or equal to 1, or 1 is less than or equal to X is how I should say that. And then we have X is less than 10. So X here is between 1 and 10, where 1 is where 1 is included in the set and 10 is not. Not that it matters because we already stated that X is an odd integer. So set builder notation is what you're listing with a variable, and then the conditions that restrict that variable to the values or to the elements, to the objects that you want. So over here we have a list of characteristics that this variable needs to satisfy in order to be considered within the set. We can also write this set like this, where we have x as an element of the integer set, such that, so what this is saying here is that x is already within the integer set. This is already a condition on x that needs to be satisfied. And then we can say x is odd and x is between 1 and 10, including 1, excluding 10. So I want you to try one now. Write the set of all lightsaber colors. This one can be done as a list. If you don't know the lightsaber colors, it's okay. Just write the 3 primary colors of light, and you're totally fine. B, write all of the sets. Write the set of all real numbers between 0 and 100. Now, this one is not possible because we're talking to write it as a list. This is not possible to write as a list because we have an infinite number of numbers here. I realize that 0 and 100 are finite, but there are infinitely many numbers between 0 and 100. Not talking about integers, I'm talking about real numbers. So this one actually, part B actually needs to be written in set builder notation. Just build the set and then use that as your answer. The union, A union B, is the set that contains all elements contained in A or B or both. Now, here, this is the union symbol. It's written as a U. A union B is, I'll give you an example, but A union B is anything that is contained in at least one of them is going to be contained in A union B. So you collect all of the elements of A, all of the elements of B, and all of the elements of both, and you write a new set and include all of those. The intersection, A intersect B, is the set containing all elements contained in both A and B. Now this sign here is the intersection sign. It's just the union side upside down. It means that you take A and B and you look for the elements that are mutually in both of them. And then you write that as your own, as a new set. So if you have an element that's only in A and not in B, it would not be included in the set. If you have an element that's only in B and not in A, also not included. The only elements that are included in the set A intersect B is the elements that are contained in both. The empty set is written this way, or sometimes we write it like this. Both of these mean the same thing. It's the set of nothing. Nothing is included in the set. It's the empty set. That's the name. Now let's do an example here. So I'm going to write out a couple of sets. We'll call the set J equal to the set Yoda, Alcestis, Grogu, Luke, Ezra, Kanan. And we'll call the set R Luke, Ezra, Kanan, Leia, Han, and Chewbacca. Right. Both of these sets, basically, we have the set of Jedi and a set of Rebels. Now let me go ahead and draw out what these are. If this is the set J and this is the set R, then we have Yoda here, who is a Jedi, is in the set J, but not in the set R. So he's going to be in the section not within the intersection between the two. We have Cal Kestis. I'm just going to write Cal and Grogu. And then we have that the elements that are in both of these sets are Luke, Ezra, and Kanan. So they would go here within the circle that is J and within the circle that is R. Ezra and Kanan. And then the elements that are in R but not in J, so outside the circle of J but inside the circle of R, would be Leia, Han, and Chewie. Okay. Now let's talk about the intersection and the union. So J union R is going to equal the set. We look back at the definition. It's a set of it's a set that contains all elements contained in A or B or both. So if you are contained in at least one of these sets, we need to write it. So we have to write Yoda, Cal, Kestis, Grogu, Luke, Ezra, Kanan, Leia, Han, and Chewbacca. Notice that these three are contained here, that are only contained in J. These three are contained here, that are contained in both R and J, and these three that are only contained in R. So when we do a union, we get a new set that contains everything in either set. And then J intersect R will be the elements that are contained in both A and B. So we look for elements that are in both sets, elements that are common between the two sets. You see Luke, Ezra, Kanan, Luke, Ezra, Kanan. None of the other names overlap. As you can see in the picture, Luke, Ezra, Kanan is contained in both the R set, the R circle, and the J set, the J circle. So this set will be Luke, Ezra, and Kanan. And that's it. They have to be contained in both. That would be the intersection. Let's move on to intervals. An interval is a set of all numbers between two numbers A and B. An open interval, denoted with parentheses, is the set of all numbers between A and B, excluding A and B. What we mean by excluding A and B is that the set does not contain A, nor does it contain B. That's reserved for the closed interval set. The closed interval, denoted with brackets, is the set of all numbers between A and B, including A and B. So here, A and B are included in the set, so they are contents of the set amongst all the other numbers that are between A and B. I want to make a note here. We only define open, and half closed. It is possible for a set to be half open and half closed. Now, these sets would be neither open nor closed. There's a more rigorous definition of open and closed if you go far enough in mathematics, but the definitions that we gave on the previous slide are enough for this class. Let's do list all of the sets. Have notation. A and B. This would be the set X such that X is strictly greater than A and strictly less than B. And we graph these on a number line. So when we have a set like this where the endpoints are not included in the set, whenever an endpoint is not included, we graph with an open circle. And then we shade everywhere for which the number is included in the set. So here, we're talking about between A and B. So all of these numbers are within the set. So we shade all the numbers between A and B. We have the closed interval, A and B. And this would be the set X such that A is less than or equal to X, which is less than or equal to B. Again, draw our number line, plot A, plot B, and this time, because A and B are both included in the set, the bracket here, and equality here, our endpoints are included. This means we graph with closed dots, indicating that this is actually within the set. And then we shade everywhere for which the number is included in the set. I'm going to run through the next few. So this one is half open and half closed, where A is included, but B is not. Then we have the opposite, where A is excluded, but B is included. So we have an open hole at A and a closed hole and a closed dot for B. Sometimes we refer to this as a hole when we have an open circle. When we get to graphing, you'll understand why. A to infinity. Now, if A is not included, so of course we have an open circle. And then we go all the way out here to infinity. Closed. A to infinity. Just as a note, infinity always has a parenthesis. You should never include infinity. Infinity is not a number, thus cannot be included in a set. It just indicates that we are going on forever in the same exact pattern that we have. X such that A is less than or equal to X. Because we have a bracket, we must have the equal sign, which means that we have a closed circle here. A, it's like that. And then we have the same exact version for B, from negative infinity to B, open, so X, such that X is less than B. We have an open circle because B is excluded. and then negative infinity to b closed, x such that x is less than or equal to b. Now, because b is included in the set, we do a closed dot here. And then negative infinity to infinity. This is also known as the entire real number line. Now, when we graph the set, you just graph the entire real number. Let's do an example here. Find set A, 3, 6, union with 4, 12, closed, and graph the solution. And B, 3, 6, intersect 4, 12, and graph. What I want to do first is I want to graph the set 3, 6 and the set 4, 12. So let's look at these. 3, 6. And these are parentheses. So we have open set here. It's like this. And then the graph 4, 12. Now, 4 and 12 are in brackets. So we have closed circles for this graph. Accidentally went a little farther. Now, I'm going to label 6 on this and 4 here, because those are the ones that are in between. For part A, what we're looking for is the union of the two. So if you look at this from a vertical perspective, I'm going to draw a few vertical lines here. Fixed. So I wanted to, if we look at this from a vertical perspective, right? 3 would be 3 here, 4 lines up with 4, and 6 lines up with 6. Now, everywhere you see a shade, wherever you see red on the respective graphs, that's where each of the sets are graphed. So 3, 6 is graphed here, and 4, 12 is graphed here. In fact, let's write that. 3, 6, and 4, 12. Now remember what these mean, what union means. Union means that we are taking numbers if they are in at least one of the sets. So everywhere you see a red shade, we're going to use that number within our set. So let me go ahead and plot this line. So note that the red line here is within the first set only. This line, because it's shaded on both graphs between 4 and 6, is contained in both sets, and then this red line is contained only in the second set. So when we do a union, we're shading everything that is in at least one of the sets. So wherever there's a red line, that's where we're going to shade. So we start at 3 because that's where the set starts with an open circle, and we end at 12 with a closed circle. This. Part B. 3, 6, intersect 4, 12. And now remember, the intersection means that we take the numbers or the values, the elements of each set that are contained in both sets. So now we're looking for where the two sets overlap. And in this case, they overlap between 4 and 6. As we can see, we have a red line here and red line here, indicating that they are contained in each of the respective sets. So we go from 4 to 6. Oops. Note that 6 is not contained within this set. It's an open circle. So we have an open circle at 6 because 6 is only contained in the second set. 4 is contained in both, so we close this circle. It looks like that. Let me go ahead and write the notation. This would mean that x, just for practice, set builder would be x such that 3 is strictly less than x and x is less than or equal to 12. And the second set would be x such that 4 is less than or equal to x and x is strictly less than 6. Just like this. That'll be it for that example. Now I want you to try one on your own. On the accompanying worksheet, try this problem. Find A, 1, 3, 1, 8, union 6, 10. And B, 1, 8, intersect 6, 10. And graph the solution. You don't need to write the set builder notation if you don't want to, although it would be good practice. I want you to notice here that my example and this try one problem are slightly different. Be careful with your open circles and your closed circles. Now let's talk about absolute value. Many of you probably have used absolute value in the past, but we need to formally define it and talk about it a bit. The absolute value of a number a, denoted absolute value of a, is the distance between a and 0. This looks like if we have 0 here and a is here, then this distance is the absolute value of a, however far that is. Now, distance is always positive. That's where we get that absolute value will be positive. Suppose b is to the left of 0, so b is a negative number in this case. This distance is the absolute value of b. It's still a positive number. The absolute value function is actually a piecewise defined function. Let's just use a for now. So this will be negative a if a is less than 0, and a if a is greater than or equal to 0. Now, with an example of this, I want you to think about it. Try to pause the video before and try to figure out these values by running it through this formulation of the absolute value before starting the video back up. So the absolute value of negative 3, since a is negative, we look at this line here. Because a is less than 0, our a is negative 3. So this will be negative a, but a is negative 3, so we get this, which is equal to 3. Similarly, the absolute value of 5 is equal to 5, because now our a is 5, a is greater than or equal to 0, so we just write out value a, which is 5. And then last, 3 minus pi. Now, to determine whether this is positive or negative, you need to know what pi is. Now remember, pi is 3.141592 rounded off. So it's slightly bigger than 3. So this value is actually negative. 3 minus pi is negative. So our a is 3 minus pi. 3 minus pi is less than 0. So our we would use the negative version here. So negative 3 minus pi. And if we distribute this negative, we get pi minus 3, which of course is positive because pi is slightly bigger than 3. Let's go ahead and do the properties of absolute value now. So 1, absolute value of a is non-negative. It's greater than or equal to 0. And as we can see, absolute value of negative 5 is equal to 5, which is greater than 0. 2, the absolute value of a is equal to the absolute value of negative a. And we can see that with 5. 5 is not special, it's true for any value. A number and its negative have the same absolute value. 3, absolute value of a product, AB, is equal to the absolute value of A, absolute value of B. Absolute value of negative 3 times 2 is equal to the absolute value of negative 3 times the absolute value of 2. The absolute value of a product is the product of the absolute values. Or same thing with the quotient. The absolute value of A over B is equal to the absolute value of A divided by the absolute value of B. If we have, say, 3 divided by negative 2 in absolute value, this is the same as absolute value of 3 divided by the absolute value of negative 2. And this problem is a little bit more complicated. Absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. So this one is actually called the triangle inequality. Absolute value of negative 2 plus 4 is less than or equal to the absolute value of negative 2 plus the absolute value of 4. And this is called the triangle inequality. Now I want to show you how this one works, because this one's actually kind of, it's kind of neat. And it's called the triangle equality for a reason. Absolute value of A, absolute value of B. Now we know that this is going to be less than or equal to the absolute value of A plus B. And we can see that because this length plus this length is always going to be longer than the diagonal. It's where the saying, the quickest point between, or the shortest distance between 2 points is a straight line. If I were to go from here to here, it would be faster to go along the diagonal than to go along B and then along A. Along B and then A would be the same thing as A plus B versus just the diagonal, which is shorter, less than or equal to A plus B. Now, A plus B is exactly this distance plus this distance. So as we if we rotate our A side, then this distance keeps getting longer and longer. This diagonal will keep getting longer and longer. But it's still always going to be less than the absolute value of A plus the absolute value of B. The only time it'll actually equal, only time equality will hold in this thing is if you have something that looks like this, where this is the absolute value of A, absolute value of B, where you have opened the triangle so that it's now flat. And then obviously the diagonal between this point and this point, which would just overlap A and B. would be equal to a plus b. Last thing I want to talk about is distance here. The distance between real numbers a and b is denoted with d of a and b equal to b, the absolute value of b minus a. We usually use this d just to denote that we're talking about distance, and then the distance between what, a and b, and these two numbers are going to be on a real number line. Doing distance in two dimensionals is slightly more complicated, but basically here we're just talking about going on a number line from point A to point B. Now, a distance is always positive, so we take the absolute value just to be sure that our number comes out positive. And try one on your own. Find the distance between -3 and 5 on the real number line. And I'll leave that up to you.